Hey everyone, my name is Bo Ingram. I'm a senior software engineer at Discord, and I'm here today to tell how Discord stores trillions of messages. We're going to talk through how Discord's message storage has evolved over time and how we've landed on ScyllaDB for our storage needs. So, work at Discord, I'm on the persistence infrastructure team, which is our fancy word for the database team. We maintain 15 or so ScyllaDB clusters. Some are small, some are big. We're going to talk about our biggest one today, Scylla messages. So, I'm a bit of a history nerd, so I want to dive right into the history of databases at Discord. On day one, there was MongoDB. Actually, it was TokuMX, which is the open source distro of MongoDB, but it was MongoDB. It was a temporary choice. We knew it wasn't going to be the right long-term answer, but it got our feet out from under us. It helped us start growing, helped us start learning, helped us start building. It got Discord off the ground. But we knew it wasn't going to be the right long-term answer. We knew that we were eventually going to have to migrate to another database. So when that time came, like, okay, what do we want? Well, we came up with some criteria for our decision. We wanted a database that was scalable. We're a growing company. We wanted a database that grows with us. We wanted a fault-tolerant DB. We didn't want to lose the Postgres database and then be completely down until it recovered. We wanted to be able to tolerate failure on a node. We wanted something low maintenance. We didn't want to spend a lot of engineering budget on spending time maintaining a database. We wanted something that we could set up and then would ideally be relatively hands-off. And lastly, we knew one thing we didn't want, which was we didn't want a blob store. Serialization was going to be expensive. To serialize and deserialize messages repeatedly, if we're going to be writing thousands of messages a second, was going to be really expensive. And we didn't want to pay that serialization cost. So looking at this criteria, we had to pick a database. Well, we chose Cassandra? Yeah, low maintenance was important to us, and then we picked Cassandra. But it was open source, it met our needs, it helped us reach that next stage of growth. Time goes by, Discord is growing. We're adding more users, we're adding more features, and more Cassandra clusters. But as we're operating Cassandra and using it in anger and learning pain points, we're looking kind of jealously at ScyllaDB. We're very curious. You don't have to tune a garbage collector in ScyllaDB because it's written in C++. Isn't that great? No garbage collection? Sounds like a dream. So let's talk about one of our Cassandra clusters. Let's talk about a troublemaker. It's called Cassandra Messages. As its name suggests, it runs Cassandra and has messages. This is a massive data set. Today at Discord, we have trillions of messages. So we have trillions of them. Well, what even is a message? So I've got here the table creation statement. This is kind of a minimal version of it. There's a bunch more actual fields, but this is basically what the minimal message is at Discord. We've got a channel ID to start with. It's the channel the message is sent on. So all our IDs at Discord are snowflake types. They're a timestamp and a sequence number, and they're sortable. Next up in our partition key, we have the bucket. A bucket is a static 10-day time window. So we use the channel ID in the bucket to partition our data in our database. We also have a message ID to uniquely identify the message. So you savvy data modelers out there might think, hey, that static 10-day time window for the bucket might make for some interesting partition sizes. Yep. So the frequency of messages can be wildly distributed. A server with 100,000 users is going to send way more messages than a server with just a small group of friends. They're also going to read more messages too, and since reads are going to be more expensive, those reads can hurt us. It's kind of painful. So the size of our data set in the access patterns cause trouble with Cassandra messages. Bunch of traffic to a data partition, that partition will get hot. When our partition gets hot, it can take latency everywhere. The partition will get tons of traffic. That traffic will cascade through the node, increasing latency everywhere. The node is degraded. But we do quorum reads and writes, so it's happening 2 or 3 times across the cluster. It's painful. So compactions start to run behind on us as well. Both Cassandra and ScyllaDB execute a process called compactions to make the data more efficient on disk. We were prone to running behind on these, which would have a compounding effect on latency because not only are you spending time compacting, which is time spent not reading data, but your data is less efficient. So it's spending more time reading that data because it's less efficient. We actually had a script we'd run called the gossip dance. We take a node out of the binary and gossip protocols to let it compact without taking traffic, bring it back in so it could get hints, and then repeat until compaction was in a better place. We can only run these on one node at a time. the other nodes would have to struggle. It actually became too expensive for us to run repairs on Cassandra messages. Ideally, you want to repair your data so that all nodes agree on what the value is for a given piece of data. But we couldn't do it on Cassandra. It was too performance intensive, or it would take too long to run. So we couldn't run it. Not ideal. Additionally, garbage collection. We had to pay that GC tax. We had to do lots of tuning to get garbage collection in shape in Cassandra. JVM tuning, JVM flags, changing garbage collection algorithms, adjusting heap sizes, all of that. There's a billion knobs to turn just with garbage collection alone. Not exactly living up to our low maintenance dreams. So Cassandra Messages is really important to us. It's a huge database that holds all our messages. Chat is a core part of our product. If messages are slow, Discord is going to be slow. So we have Cassandra Messages. So in about 2020, this is kind of the state of the architecture. We have this Python API monolith that talks directly to databases. We actually migrated all our other database clusters over to ScyllaDB, except for messages. Well, why haven't we done messages? I mean, it's so important. Why is it still running Cassandra? Well, we wanted to figure out ScyllaDB. We didn't want to learn all our lessons with our messages database. We wanted to gain experience with our other clusters. We wanted to figure out how we could get the best possible performance. We felt there were performance gains to be found, both within the database and our setup of it, but also in the code calling our database. So how can we let the database be its best? Well, if we make the code talking to Cassandra more efficient, we'll gain even greater benefits when we switch to ScyllaDB. So we wrote a thing. We call it the data service library. We wrote a message service that served as the prototype for it to explore ideas that eventually became the data service library. One of the really cool things about it is it's written in Rust. Well, why Rust? I mean, not just because it's cool. There's actual reasons behind it. We had some experience with it. We used it for a few use cases previously. We used it in Elixir native implemented functions to speed up some hot paths in our real-time systems. We'd recently rewritten our read state service in Rust as well, and found great performance benefits with it. We found it really just an enjoyable language to write in. It's fast and it's fun. It does what it says. We love getting those C, C++ speeds and not having to deal with garbage collection. When we rewrote our read state service, we'd done it in Go previously and ran into GC issues there. Writing in Rust, no garbage collection. We really don't like garbage collection. But it's fast, it's fun, the language constructs are nice, it's enjoyable to write. When we deploy Rust code, it generally works. Rust likes to tout that it has fearless concurrency, that you can write concurrent code without fear. The borrow checker and the type system enabled us to write safe and fast concurrent code in our data service library. It has strong Cassandra and ScyllaDB support as well. We're able to use the Cassandra C++ crate talking to Cassandra, and we're working on switching to the Scylla Rust driver today that Scylla supports. So we get the great native driver support, which is awesome, especially with ScyllaDB. We also get to leverage the Tokyo ecosystem. Tokyo is one of the big Rust libraries that it likes to tout, that it likes to talk about. It's big in the Rust ecosystem. So Tokyo is an library for async I/O, which we leverage heavily in our data service. It lets us write the library that we want, that performs the way we want. And most importantly, it lets us say we rewrote it in Rust. It's always good to get those meme points. Always good to be able to say we rewrote it in Rust. So, we talk about our Cassandra problems. Well, looking back, what were the problems we were struggling with? We were having high traffic to certain partitions, causing cascading latency. So each query becomes slower and more expensive. So how can we lessen this? Well, we wrote the message service to protect our database. It sits between our API and Cassandra, it talks via gRPC, and it queries the database for us. Its role is the protector. So the big thing it does for us is request coalescing. If multiple users are requesting the same row at the same time, we'll actually only query the database once. Requests will come in and subscribe to a worker thread. And when that request completes, the worker thread is going to call the database. The worker thread will then return the result of that query to all of the gRPC requests that have come in that have subscribed to it. So we can take all these requests coming in and reduce it down to just one query on the database. Rust was super helpful here. It made it easy for us to write safe concurrent code to power this. So if we have a large server, it's got tons of users on it, the server makes a big announcement and pings everyone. Users are immediately going to go read that message. They've just been notified about it. They're going to pick up their phone, tab to the app, look over on their computer, and hey, I'm going to go look up this message. So instead of like a huge burst of 1,000 queries going straight to the database, making the partition hot, causing Cassandra to fall over, we can reduce it down to just that one single query. The request will come in, a worker thread will be spun up to query the database. The request will subscribe to that worker thread as they come in, as the additional requests come in. They'll subscribe to that original worker thread. The worker will query the database and return that announcement message to everyone who's requested it. This really helped our Cassandra cluster. We reduced traffic down to it a lot, especially with these hot patterns. So just one query? That seems very small. Well, it kind of leads to the second part of this. The second part of the magic is actually upstream of message service. Consistent routing. We route requests to our message service based on the channel ID. We can pick any routing key, but for this case, we've chosen channel ID. So all requests for a specific channel go to the same message instance. So in our big announcement scenario, if everyone goes to load that message in that channel, all those requests go to one single message instance. Rust is super performant and lets us handle this case without breaking a sweat. It's awesome. So we get all requests for a specific channel going to the same message instance. And then with the power of request coalescing, we can get the best coalescing we can because all requests are going to that one instance. So that really lessens the load on our database. It helps a lot. It doesn't solve all the problems, but it helps a lot. Incidents go down, but not away. We're still having issues, just not quite as frequently. While this is happening, we're gaining more experience with ScyllaDB. We're learning how it operates, how it runs, how to tune it, how to make it perform. We want the best ScyllaDB we can have so that Discord thrives. But what does that mean for us? Well, in a database, we want both speed and reliability. If messages are slow, Discord is going to be slow. If messages are down, Discord is going to be down. So to accomplish this, we've architected a storage solution we refer to as the super disk. It gives us the best of both worlds, both speed and reliability. So we run our databases in GCP. In GCP, we've got two big options for our disks. We can use local NVMe SSDs, which are fast, quite fast, or persistent disks, which are persistent. So the local NVMe SSDs are attached directly to the underlying instance. Since it's right next to it, it's very, very fast, and the disks are fast themselves. That's why it's ScyllaDB's preference, and it's what they recommend. But we found, running it, that in GCP, the local NVMe SSDs were actually quite unreliable. They were prone to crashing, having disk errors, which meant, we'd lose the disk, and there would be increased risk of quorum loss and downtime in our cluster. Traditionally, we like avoiding downtime. So, we're very hesitant to use those. Additionally, if the underlying host had an error, because the disk is directly attached to it, there's the potential for losing the data on the disk as well. GCP does try to migrate it for you, but we found that in many instances, we would lose data on the disk. Not ideal for a database. We prefer using our GCP's persistent disks. They give us point-in-time snapshots, which is kind of the cornerstone of our backup strategy, but the downside is they're slow. They're abstracted over a network, so accessing the disk is going to require a network call, which is going to be slower. If we ran these in production, just these, we were going to have the same cascading latency issues. We were going to have reads that were going to back up and be slow and take down the rest of the cluster. Not ideal. So GCP says we got to pick. We can either have these local NVMe SSDs, which are very fast, but unreliable, or we can have good old reliable persistent disks, which are probably too slow to meet our needs. GCP says we got to pick. We say, no, Linux says we can have both. So we leverage RAID in Linux to get the best of both worlds. By architecting this topology we refer to as the super disk. So we start off with a persistent disk of about 1.5 terabytes. We then take 1.5 terabytes worth of the local NVMe SSDs and stripe them together via RAID 0. With RAID 0, this gives us a large logical volume equivalent in size to the persistent disk. We then can take this new logical disk, the RAID 0, and combine it with the persistent disk via a RAID 1 array. Well, what's RAID 1? RAID 1 lets us mirror the disks so that the data on the RAID 0 local SSDs that are striped together matches the persistent disk. So it has the same data on both the persistent disk and the local NVMe SSDs. Then we mark our persistent disks in RAID as write mostly. This means that reads will go to our RAID 1 array, reads to our RAID 1 array will be predominantly served by the RAID zeroed local SSD side of things, not the slow persistent disks. So the RAID array will send our reads to our fast local NVMe SSDs. So this is RAID. This is our RAID setup, our hybrid RAID superdisk. Let's kind of look and see how it performs in a few scenarios. So a read comes in, goes to the RAID array, says, okay, this is a read. The persistent disks are marked as write mostly, so the local NVMe SSDs should get the read. They're fast. We get speedy reads. Yay, speed. Writes. When a write happens, RAID says, okay, we want these two disks are mirrored together. We want them to have the same data. So therefore, write should be mirrored to the local NVMe SSDs and the persistent disks. When we mentioned host errors, what if the underlying host has an error? Well, we're probably going to lose the local NVMe SSDs we found. When it comes back up, that data is going to be gonzo. It ain't going to be there. But because it's mirrored, it'll still be on the persistent disks. So we still have a copy of it, and we get that durability and that persistence. Then, when it comes back up, RAID will say, oh, wait a minute. These local NVMe SSDs that have no data are supposed to match the persistent disks. And it will handle mirroring the data again, executing a recovery operation to resync data from the persistent disk to the local NVMe SSDs. This gives us everything we want. We get our speedy reads because they go to the local NVMe SSDs, and we get durability because it mirrors all writes to the persistent disks, which will not get wiped on a host error. But, we turn it on. It doesn't work perfectly out of the box, of course. We see that reads are actually still occurring at the speed of persistent disk writes. We dig in, look around, do some research, find out that ScyllaDB uses one I/O bandwidth channel by default, which is shared by both reads and writes. What this means is that we'll be limited by the slowest operation, the persistent disk writes. When we worked with ScyllaDB, we're able to get duplex I/O implemented, which gives us a separate channel for reads and a separate channel for writes. They each can have their own bandwidth. That means we're no longer limited by the persistent disk speed when doing reads. Still get our speed, yay. The write intent bitmap is also a problem point for us. The write intent bitmap speeds up resyncs and recoveries, but we found that it was too expensive to maintain. We had massive latency. I/O would back up. It would cause trouble. So we turned it off. We'll talk more about how this helps reduce complexity in a second. So complexity, you might think, hey, this sounds awfully complicated. Well, the superdisk makes for a system that's fast, scalable, durable, and complex. We try to reduce that complexity as much as we can. Automation and logical simplicity help us out a lot with this. Can we reduce the number of states the system can be in? If we can, that'll really help simplify things. We try to bias, when we run into unknown scenarios, towards removing and replacing nodes. ScyllaDB gives us this primitive where we can replace a node in the cluster, and the other nodes will stream data to it. We can leverage that to simplify some of the more gnarly RAID operations in the event of an error. I mentioned the write bitmap. Yes, having it gives us faster resyncs, but one, it's too expensive to maintain, and two, if the errors you see in the resyncs that are triggered are either minuscule resyncs, which are tiny and going to happen basically instantaneously, or a full rebuild that's going to require streaming all the data no matter what, then really, what advantage does it give you? Being able to remove the write bitmap really helped us out. It helps reduce complexity there. I mentioned trying to reduce the states the system can be in. I think a good example of it is the pre-flight script we run before our database starts up. So the pre-flight script runs, and it's in charge of giving ScyllaDB the green light, saying, hey, everything's good. You're good to start. You're good to go. So we think of it as 3 states. In our first state, it's a brand new node. The RAID array hasn't even been provisioned yet. Well, in that scenario, we need to provision the array, set everything up, set up the RAID array, and then tell ScyllaDB, hey, you're good to go. Maybe it's a new node, maybe it's replacing a node, but we give it the green light to join the cluster. Our second state is if there's data on the persistent disk, but not on the local SSDs. In this scenario, there's probably been an unclean shutdown. The underlying node has had a host error. We've lost data on the local NVMEs, so we need to recover it. Our pre-flight script handles waiting and saying, hey, actually, there's a recovery operation in process. Let's wait for this to complete before we turn it back on, before the node starts up. Our next scenario is there's data on both the persistent disk and the local NVMe SSDs. In this scenario, we've probably just restarted the database or something. This is an easy scenario. You just double check, make sure everything looks good, health check the RAID array, check the state of the system. Everything's great, hopefully. Tell ScyllaDB it's okay to start up. So yeah, this is our hybrid RAID super desk. It gives us both speed and reliability. We put a blog post out a few months ago about this. Feel free to check it out. It goes into greater detail about it. It kind of goes into the design process as well, and how we came up with it, how we architected it. But yeah, this hybrid RAID super disk gives us both speed and reliability for our ScyllaDBs, which is awesome. We've laid the groundwork here, right? We've set up this data service library that optimizes our database accesses, optimizes our code that calls our databases, makes that more performant. We've come up with a super disk storage topology, which gives us both speed and reliability for our databases. Meanwhile, we technically are still running Cassandra at this point, and it's a high toil system. It's causing a lot of trouble. It's a pain. It's time. It's time to get rid of it. It's time to migrate trillions of messages to ScyllaDB. So how do we do it? What's the plan here? Well, Cassandra is painful, and we want to get value quickly because Cassandra is giving us literal headaches. I had a migraine that I refer to as the Cassandra migraine because it popped up after a couple of days of intense Cassandra firefighting. So we want to get value quickly. So we come up with this plan, try to use ScyllaDB for recent data, migrate historical data behind it. Sounds complex because, what every project needs that you want to get done quickly is complexity, right? We've set up ScyllaDB Spark Migrator. It requires a lot of tuning. It's going to take a while. Our estimated time completion was at least 3 months away. That didn't sound amazing. We didn't want to wait 3 months to still be firefighting Cassandra until we could get value from Scylla and start getting it completely used. So we're like, okay, can we do better? So plan V2. All the goals of plan V1, but get value even faster. So we sit and think, we're like, okay, well, we've written this huge data service library that's optimized our database accesses. Can we leverage it here? So we engaged in some meme-driven engineering and rewrote it in Rust. We re-implemented the Scylla data migrator in Rust in an afternoon. 2 of my colleagues sat down and did a little code jam and updated our data service library to perform data migrations, including Stephen Ma, who is speaking later today on our key value store. So they re-implemented the data migrator in an afternoon. It reads token ranges from Scylla, or from Cassandra, checkpoints it locally via SQLite, and then just fire hoses them all into ScyllaDB. So we originally had a 3-month estimate for this project based on the original migration time. We got it done in 9 days with our new migrator, up to 3.2 million messages per second we would burst up to. Got it done quickly. Awesome. So we performed data validation and verification once we got all the data over. We sampled random reads, made sure that data was consistent, made sure they're equivalent, made sure the data was correct. Things are looking great. Meanwhile, while we're doing this, we're also firefighting Cassandra. That's, it's a dumpster fire. So we happen to have a team on site. We're all together, and we decided to go ahead and flip the switch. We gathered together. We ate cake. It was really good cake. There's nothing like cake after completing a project. Got it together. It's been running ScyllaDB since then. So this was May 2022. How's it been since then? Well, it's been great. It's been quiet, knock on wood. I'm on call right now, so I would encourage you all to knock on wood so I'm not cursing myself. But it's really been great. It's much more efficient. We're able to run fewer nodes with ScyllaDB, less than half the nodes of our Cassandra cluster because it has better storage density. It's also got more efficient disk utilization, 53% reduction in disk usage across our cluster. And no, we didn't delete half the messages. It's just much more efficient. With better compression and other improvements in ScyllaDB, we're able to halve our disk utilization and the number of nodes. And additionally, it's much more consistent. Latencies for historical message reads in Cassandra were anywhere from 5 milliseconds to 200 milliseconds. With ScyllaDB, they're 5 milliseconds almost every single time. Every single time. Not even almost. I'm not hedging on that. It's 5 milliseconds on the dot. No microseconds going over later. I'm going to be specific here. It's great. It's much more consistent. So we just had the World Cup. We learned very quickly. Goals scored will show up on our message send graphs via spikes. This is cool because, it's cool to see real world impacts of things on your systems for good, for positive. But it also meant that it was okay to have the World Cup on during meetings because you were checking our infra, monitoring for problems, being proactive, not just watching the World Cup. So what I have here is a graph of relative message sends from the World Cup final. Huge match. I mean, not only is it the World Cup final, but it's Argentina versus France. Lionel Messi, the best soccer player of all time, is attempting to check the last box of his career and win the World Cup. He's going against France, led by the supremely talented Kylian Mbappe. Lots of hype for the match. They lived up to it. The really cool thing here is we can tell the story of the match based on the spikes in the graph. So that first spike, Lionel Messi hits a penalty. Argentina goes up 1-0. The second spike is a beautiful counterattack for Argentina. They go up 2-0 before halftime. The next spike, which is kind of more of a plateau, if you will, it's halftime. People are chatting. Spike lasts for about 15 minutes. Halftime lasts for 15 minutes. People are chatting, catching up. Wow, that was crazy. Hope Argentina can hold on. I hope they come back. Yeah, so match goes on, and suddenly there's this big spike. France scores twice with 10 minutes to go. Ties it up. If no more goals are scored, we're going to extra time. Argentina was 10 minutes away from winning the World Cup. France has come screaming back to tie it. So there's no more goals in regular time, so we go to extra time. That's the next spike, and there's a smaller spike up ahead because it's halftime and extra time. Well, it's going to get more exciting, don't worry, because shortly after the second half of extra time, in our next spike, Messi scores. Argentina takes the lead. They're minutes away from winning the World Cup again, but oh no, France has scored again. France gets another penalty and ties it up. It's tied. We're going to penalty kicks. So the next spike is the end of extra time, but it doesn't really return to normal, right? We see it just kind of growing and growing. Penalty kicks are happening. Excitement is building. People are getting stressed. People are cheering. People are in anguish. Are you Argentinian? Are you French? And then France misses a penalty kick or two. Argentina wins. That's the last spike. People, oh wow, Argentina won. People chatting about it. Seeing that huge spike. I'm on the couch stressed watching things. I vividly remember realizing that my heart rate was fairly high for an event that I was not super invested in. But meanwhile, Discord and Scylla messages aren't breaking a sweat. We're way up on message sends and we're doing amazing. So this was the story of how Discord stores trillions of messages. With our data service library written in Rust, our hybrid RAID superdisk, and ScyllaDB, we handle trillions of messages and provide a place for you to chat about anything, anywhere, anytime. If this work excites you, check out our careers page. We're always doing interesting things, so it's an exciting place to be. Thank y'all for having me today. I'm going to plug my colleague Stephen Moss talk later today. He's talking about our key value store, which is key for us and has some novel storage solutions, and it's beloved by our product teams because it helps them move quickly. Best of both worlds. Yeah, thank you for having me today, and enjoy the rest of the conference, y'all.